Okay, we can get started now, I think. This is going to be a full session, so we probably get a couple more folks coming in, maybe a little bit on the wait list. So it's good you got a seat. I'm glad that you got in here. Awesome stuff. My name is Richard Lacone. I'm from the Bay Area, California. A little bit jet lagged, not too much. But you're in the Introduction of VXLAN session, the future path to your data center. Okay, this is a 1000 series. So it's meant to be an introduction. And typically what I like to do is really give an explanation of why we're actually talking about VXLAN today. A little bit about myself. I've been with Cisco since 2001. So if you look at my directory picture then versus now, you may not know who that is. But what I want to talk to you about, I'm from the Data Center Networking Business Unit. I'm a principal technical marketing engineer. And essentially what we do is we build the Nexus product line. And we run NXOS, and we essentially kind of, Nexus dashboard. And that's the business unit I'm in. And I'm in technical marketing. So once we get the doors shut, I think we'll go ahead and get started here. Quick housekeeping rules. I'm sure you're going to see this slide in every Cisco session you attend this year. And essentially what this is this is the way we can kind of communicate post-session. Now, I'm not going to be able to answer questions live as you guys type them in, but I can share some goodies. I can share additional white papers, configuration snippets, guides, whatever you guys need. Please subscribe to this WebEx channel. And we have moderators also here. So some of my colleagues are also moderating. So if you have any questions, recommendations, solutions, suggestions, feel free to ping on this channel. I'm also going to be part of the Meet the Engineer. And if you have any other questions, design scenarios, deployments, some guidelines, any type of prescriptive guidance, feel free to schedule with me. I'm here all week. Okay? So this is the session abstract. Now all of my slides look like this. Just kidding. No, this is a lot of text. But really what this is just to really explain, as I mentioned before, how VXLAN is the de facto standard for data center encapsulations. And essentially what I'm going to do is really kind of talk more or less about that. But we're talking about a data plane encapsulation. And with the data plane, you also need something called the control plane. The CPU, the processing, the way I educate and inform of what devices are connected to me. But what I'd like to do is I made this last night. And what this is I looked at the enrollment attendees, and I wanted to kind of categorize based on the attendees here of who's actually in the different sectors, whether it's technology, financial services, media. So you're going to see a bunch of different, and these are the colleagues next to you here. But really what I'd like to say is thank you for coming. Because I think it's important for us to kind of establish and share this knowledge transfer based on what I've learned from theory and also practical within the lab. So we're going to spend some time talking about the VXLAN encapsulation, and we're going to talk about the evolution of the data center. Okay? Now, it's important for us to understand because overlays have been around for quite some time. So we're going to talk about the need for overlays, but really, what is the VXLAN encapsulation? I'm sure everybody here has configured a VLAN before, correct? Everybody knows VLANs. So if we had VLANs, why did we need VXLAN? What did that bring to the table? And then with just a data plane encapsulation, it works, but you need to have that tight coupling of the control plane. And that's something what we call EVPN in the data center. So really, when you start thinking about VXLAN, you kind of hear VXLAN EVPN running in a data center fabric, maybe in a single site, maybe in a multi-site environment, but that's essentially what you're going to be using as your underlying technology for that architecture. And then what I'd like to do is do some packet walks, kind of show you the communication after we establish a foundation, but go through the mechanisms between a layer 2 and a layer 3 kind of workflow. Does that sound fair? All right. Now, bear with me for about 10 minutes, maybe 15, we'll see. But we have to understand why. As with every engineering kind of understanding, there's always a why. And really, what was the reason why we did VXLAN is about the evolution of the application architecture. So I'm going to date myself. So when we see the original way of development for application architectures, it was very much of a monolithic written approach. So we used to have these really big servers. How many of you out there may remember something called Windows NT? Okay, cool. Just taking a shot. Novell, NetWare? All right. My group, I like it. CD-ROMs. Okay. But that's typically how you would install these servers. And these were big, beefy servers. Kind of where you would have a lot of compute, a lot of memory, storage, a single NIC. And that's what your application was written for. You had a user interface, a business logic that was rendered, and then an ultimate database. And that's typically how we would use these applications in the data center at this given time. The reality of this is sometimes these servers, while they were big and beefy and the application was running, they were underutilized. So sometimes you could see that maybe it's only a percentage utilized for the compute power, the memory, the storage. Not only that, is if this server failed, that's a pretty big lift and shift to replace it. And so imagine now I have a single application, which in the networking world would be a single MAC address, a single server, and a single NIC. But as I fast forward, because what we wanted to do was really introduce a level of efficiency. Now, how can I take that big server that was a single monolithic entity, and what we saw was the evolution of the way the applications were written. Now it was a distributed application, where maybe I could have, instead of one single entity doing one thing, I can split it across to do multiple functions within the application, the way it was developed, the way it was written. Hence, there was a need for something called a virtual machine. So I was able to take that server and now compartmentalize that to have different virtual machines or VMs within a server that can now share the compute, share the memory, share the storage. And with that, from a network perspective, instead of a single IP address that would map to that application, now I have multiple MAC addresses, multiple IP addresses on a single physical infrastructure. So this was actually the birth of virtualization from the application world. And if you fast forward that to even what we're seeing now today for cloud native microservice architecture, now we're seeing more development on containers. We're seeing Kubernetes, Docker, and these are much more lightweight than a virtual machine. They can boot up much quicker. And sometimes these are short-lived, sometimes they're long-lived. But now instead of I'm doing more lightweight HTTP calls, API calls in the back end. And this is essentially, as you saw, the evolution of the application architecture, starting from a monolithic to a distributed to a microservice approach. Does that make sense? And with that, you kind of had different traffic patterns, right? From the monolithic approach in the data center, this was really more of a client-server type of connectivity. And that translated to more of a north and south traffic pattern from the data center to the outside world. And then when I see the web applications, now what you see now in the back end of a data center was more east and west traffic, right? Say, for example, when you go to a store and you're making a purchase, you're swiping your credit card or ATM card, there's a back-end system that's authorizing the validation, checking the funds. There's multiple applications happening, communicating east-west within the data center just from that single call. And that's essentially what we started seeing as these data center technologies evolve from the application approach. And the same thing what we did see with the microservice architecture was just more east and west traffic inside the data center. So that's what the important part of is. We needed a different type of network to handle the needs of the application. And you really think, from my experience, I always thought the servers kind of led the network. Because whatever the servers did, the network had to follow. And we had to make sure that we can optimize and leverage the way those applications were written. How is the network going to be able to support that? So we had an evolution of the data center network. Who has seen something like this before? Quick show of hands. What is this right here? Spanning tree loop. Spanning tree loop. How many of you out there have actually had a spanning tree loop that you troubleshot? Quick show of hands. Who liked that? Yeah, exactly. You like I remember doing it. It was even in the lab, plugging something in, and then all of a sudden it was like Christmas. Lights flickering fast, CPU utilization, show process, CPU sorted, show root guard, BPDU guard, loop guard. These are all your spanning tree toolkit. We need those. But this is what we did. We kind of still do from time to time, but we had to have this protocol to make something loop-free, right? So this is the kind of, if you think about that era of monolithic, this is kind of the data center topology that we had back then, a 3-tier architecture, access, aggregation, core, where your access to ag was primarily layer 2, and then your ag to core was layer 3. So for my hosts, my endpoints, a lot of the times my default gateway was sitting at the layer 2, layer 3 demarcation at the aggregation layer. That was my boundary. So a lot of the times I'd have to trombone my traffic when I went to layer 3. Not only that, is if you can see the illustration here, what do you notice? There's a solid line and there's a dotted line. The dotted line is to represent we have a blocking interface. Because if you think about it, this could be a switch, 48 port, 10 gig, 25 gig on the southbound, but maybe I have my northbound uplinks, but now I'm blocking some. I'm not getting the most use out of my switches because I'm using spanning tree and I have to block this topology. There's a few chairs up front if you want to sit down. Thank you. So we had this kind of very kind of legacy, and it worked for its time, but we needed something to evolve for those applications, as I mentioned. Now, how did we get around the spanning tree loop configuration? Most of the technology in the industry was introducing something called MLAG, or MCLAG, multi-chassis link aggregation group. Now I can take 2 physical switches and have a port channel, so now I can have active-active uplinks. Cisco had something called VPC. Who out there has VPC running on the networks today? Right? Very, very common, your virtual port channel. And this is essentially what we did to evolve based on the spanning tree, but VPC is only limited to 2 switches, right? What if I have 4 switches, 6 switches, 8 switches? So we wanted to make sure we can scale horizontally to support things like vMotions, VM mobility. So while it served its purpose, we still weren't there yet. But what did Cisco do? Okay, looks like there's a hidden slide. Oh, what Cisco did, seems like there's some slide that may be hidden, but we introduced a technology called Fabric Path. Do you guys remember Fabric Path? Anybody have Fabric Path running on the network at some time? Essentially what Fabric Path was, a way to use layer 2 multipathing using a Fabric Path header and having point-to-point links and leveraging Fabric Path as a data plane encapsulation with ISIS running as a control plane. And it worked for a lot of customers. However, it was a Cisco proprietary technology, so it was never vendor agnostic. So sometimes customers, if they were all Cisco, they could deploy it, but if they had mixed environments, they couldn't. And a lot of the times, sometimes customers do have a dual vendor strategy. So they wanted a common operational model, and that's essentially what we did is we created something called VXLAN. Now, as I mentioned before, imagine now that we created this network of east-west traffic, and we introduced something called leaf spine two-tier architecture. So we're no longer going to that three-tier architecture of access, aggregation, and core. We essentially have a two-tier leaf spine architecture that was really developed to really understand the traffic flows to be very deterministic, low latency, single hop, right? And so there was a gentleman in 1953, his name was Charles Clow. So who here has heard of a Clow fabric? Sometimes they say cloths, but essentially what this is this is the two-tier fabric. Now, I'm giving an example of the different stages because we have here different stages within the pipeline where ingress, there's the middle stage and an egress stage. So when I used to work on modular chassis systems. So that's when you had line cards, fabric modules, etc. Catalyst 4500, Catalyst 6500, I had that. And this is, when I see this, this reminds me of that, where the ingress could be slot 5, my middle stage is a fabric module, and then my egress could be something, a port on slot 6, and that's how the traffic traverses. Similar concept here, where we have input, middle, and output stages to make sure that we can have deterministic and non-blocking architectures. So what am I telling you is we had to kind of build a new architecture to complement the data plane encapsulation of VXLAN to really get out of that three-tier legacy, tromboning of traffic kind of mechanisms to something more two-tier and efficient. And so we took that kind of three-tier architecture. Now we built this is a folded Clow leaf spine. What you have essentially here is just an example of some pods, but you can see here how every leaf is going to be connected to every spine, right? The leaves aren't connected to each other. But this is what allows us to be much more efficient and have better latency and better deterministics when you have your traffic patterns coming in through the multiple stages within a data center fabric. So as I mentioned before, we had an overlay technology. And overlays are essentially, encapsulations. And we'll talk about that in some upcoming slides. So we introduced this fabric path MAC and MAC capability. But then what we also did back in 2014, we introduced VXLAN. That's 11 years ago. And look at how many people are in this class. I love it. So this was essentially, we created the data plane encapsulation, RFC 7348. And if you read the RFC, you're going to hear a lot of this stuff that's in my session pretty much coming out of that RFC. And really what we did is we created something with this VXLAN fabric where we can have leaf spines and maybe core networks if we needed to go up north, or border gateways. Essentially, we're leveraging a MAC and IP encapsulation. But now what we did, though, is this is just something called flood and learn. What does that mean? Who here remembers something in Ethernet called CSMA CD, right? Collisions, broadcasts, flood and learn. If I don't know where you are at, I'm going to shout. So I want to make sure everybody can tell me, hey, where's the location of this particular IP address or MAC address? I need to share that and build a table topology in a database. So what did we do? So what we did is we knew that when we started seeing these challenges of the way the three-tier architectures were giving us at that time for those particular applications, we saw spanning tree, while it's a great algorithm protocol, it does require convergence time, right? If there's a topology change, there's a topology change notification, that port is going to transition from a blocking, a listening, and a forwarding, right? That could be 30 seconds. And so we needed something to be much more quicker, to be much more efficient, to be able to capitalize on those benefits. And then what we wanted to do is get away from those unused links. How can I make sure I can have active links, leveraging something beyond VPC to really get out of that limitation of just 2 switches? And so I wanted to make sure I can have the best type of forwarding and the best type of delivery, but ultimately scale. So that's why we had these challenges. And so we needed to create something with overlays. Now, overlays are not new. We had overlays for many years. IPsec, MPLS, GRE, right? These are all overlays. We use overlays all the time. Who has a VPN client on their laptop, right? And we have to go over the internet, that's an overlay. And really what the overlay is an encapsulation. It's a wrapper around the packet to make sure it can traverse over an existing fabric, but have some level of site-to-site encryption, segmentation, isolation, etc. So this is essentially some examples of some overlays. Now, when I learn new technologies, I like to kind of deconstruct the different components. And this is essentially, when I look at an overlay taxonomy, what does it really mean? It's a tunnel encapsulation. But there's some services that I want to make sure I can support. Maybe I want to support layer 2, layer 3, or a blended service to do both, something like integrated routing and bridging. And then ultimately, I need to have what we kind of built as an underlay network transport, a layer 3 fabric. Because I want to make sure with my overlay, I can send traffic across the underlay without having to reconfigure anything, because the underlay is my highway. So imagine really the streets of the underlay are like a highway, and the overlays are like maybe some shipping trucks that want to use that to go to different destinations. And with that, with the technology, we have to use a control plane and a data plane. We have to learn, we have to forward, and we have to do it very fast. So what are some overlay services? As I mentioned before, a lot of these applications required something called layer 2 adjacency. So what does that mean? So in typical Ethernet fashion, we wanted to make sure that the applications could maybe communicate as if we were on the same LAN segment. Bus topologies. We wanted to make sure that we can actually, how do we create that, but maybe we're in another rack, we're in another data center, we're in another pod, we're in another city. How can we simulate that environment to make sure that we're adjacent to each other to communicate? Because that's what the applications dictated and required. So if you think about the way the layer 2, there's pseudo wires, there's virtual endpoints, there's tunneling, but we need to route because some traffic needed layer 3 optimization. So we wanted to make sure we can do routing and bridging. And that's essentially what you see here is having a mix. Can I have a device where the interface supports both routing and bridging on that port? And that's what we needed in an overlay service. Now, tunnel encapsulation is pretty straightforward, right? As I mentioned before, I think of a tunnel encapsulation as envelopes within envelopes within envelopes, right? All with different destination source IP addresses. And so you can see here is some examples of a layer 2 tunnel encapsulation. Maybe you have something like an MPLS layer 2 VPN or something called Q&Q, which we see in our service provider customers where they can do a customer edge .1Q that's mapped to a provider edge .1Q. And those are different encapsulations for that. And in layer 3, obviously, we have MPLS layer 3 VPN. We have IP generic route encapsulation. And also we have something called Lisp, which is our control plane for software-defined access for location identifying separation protocol, Lisp. Now, in order for the overlay to communicate, it has to have a solid foundation for layer 3. And that's the underlay network transport. So you can build an underlay with layer 2, but most everybody builds it with layer 3. And what I mean by that is you have routing protocols now to have reachability between the endpoints, leveraging something like OSPF, ISIS, or BGP in my underlay to establish that level of connectivity. And so once we have that underlay built, then we can essentially create an overlay to support the virtualization of the network. So that's essentially what we're doing. Everything we learned from the servers and those applications, we modeled that, and then we evolved the network to kind of adopt to support virtualization and really give things like a control plane in the system, because now my device needs to be able to learn. And whether I need to learn, I need to know if somebody's locally attached or maybe somebody's remotely attached to another interface, to another peer, but we need to make sure we have all that communication we can share with one another. And then as we introduce route distribution, connectivity, how do I do it? As I mentioned before, in the past, flood and learn was much more dictated on the flood and learn. We use multicast or broadcast unknown unicast, and that's essentially how we did that. Or we use something more elegant like BGP, which runs on the internet. And then peer discovery, if I want to know where my peers are at, I need that control plane to give me that intelligence. So if you think about the switching hardware, this is really what the CPU is doing. The CPU is building the control plane to have all this information, the state, and these tables and these databases. But it needs a data plane. And when I think of the data plane, I think of the switching ASIC. In that ASIC, I see where the encapsulation is built, where the unicast forwarding comes into play for layer 2 and layer 3, and where I can support things like a broadcast, unknown unicast, and multicast. Broadcast is ARPs, all F destination. Sometimes it's DHCP discover packets. We need to make sure we can transport those over this new network. So essentially what we did now is we introduced something called VXLAN. So VXLAN is a standards-based encapsulation based off RFC 7348. What we did instead of Fabric Path, which was MAC and MAC, now we're taking that MAC frame and encapsulating that into IP, and more detailed, this is UDP, the User Datagram Protocol that we're all familiar with through layer 4. So this is essentially what we did to build this data plane encapsulation. And then what we wanted to do is we wanted to make sure that it was transport independent. What I mean by that is if I built a layer 3 underlay, I can actually bridge across it if I needed to support that layer 2 adjacency between the applications. And what I was able to do is because of this transport independence, now I can support that blended service for integrated routing and bridging. And because I'm using UDP encapsulation, something that I was able to do now versus GRE, which is using just IP, is I can give per flow entropy. Now, what does that mean? Because I'm using UDP, I have the ability to actually spread traffic evenly across different ports because I have a level of entropy that shows some uniqueness and variability. Has anyone heard of something called polarization? Okay, so what polarization is, imagine if you have 4 uplinks and you're sending 100 gig of traffic and you want 25 gig to go across all 4. If you don't have the randomness of traffic entropy, most of the traffic is going to pick one link and it's going to go over just one link, while the other 3 links are sitting here kind of idle. So what I want to do is make sure that I get 25 gig across all 4 links. Therefore, I need to have some hashing in the ASIC to be able to support that. This is what VXLAN is giving you. This is what's in the RFC. And this is what's important to understand. And then last but not least, because VXLAN is giving me additional segments, what do I mean by that? If I talk about VLANs, I was talking about maybe 4,000 VLANs based on that particular identification. Now, if I'm using a 24-bit field, I can get 16 million segments using VXLAN. That doesn't mean your switch is going to support that many segments. What that means, though, is your fabric is going to be able to support different VNIs, virtual network identifiers, so there's no collisions on the wire. And that's important because we're using a new technology called VXLAN. Now, let's take a look at the underlay taxonomy. Now, if you read the RFC, there's definitions of these particular entities. So you may see the word VTEP, virtual tunnel endpoint, or you may also see it interchangeably used as an NVE, a network virtualization edge. So what you see here is, imagine here, now this is a virtual machine. Now I'm plugging into a particular VTEP switch, and this is what the V is here, and this is my edge device. So what I'm building is point-to-point layer 3 links. These could be my spines. Wow. Okay. Let's see here. Let's get back on track. Okay. And so what this is actually doing is showing you an example of the underlay network that I'm being built. So I'm building the fabric. I'm building that underlay network because what I ultimately want to do is once this is built, locked and loaded, then I can introduce the overlay. Now look at the picture of the underlay where I can have different links going across east, west, north, and south. But on my overlay example, it looks like a bus topology because now it's making it look like everything's layer 2 adjacent because I'm able to leverage the layer 3 underlay fabric to support those overlay services. And that's essentially what we're introducing. So I can introduce different service identification based on, instead of a VLAN, now I have something called a VNI. And that's what's going to make sure I can have that isolation, a new identification, a flexible namespace of how we can actually segment. So here's the VTEP. Now the primary role of a VTEP is to take the Ethernet packets coming in, or the Ethernet frames, I should say, and then encapsulate that into a VXLAN frame. And really what you think about that is if I have VLAN, say, 100, and I have these two entities in VLAN 100, I can map that VLAN 100 into a new VNI across the fabric that could be another identity. So that could be VNI 10,000. And essentially what I'm doing here is just encapsulating with that, and this is essentially how we're building this out. So a VTEP essentially is going to have its own loopback interface for the virtual network. It'll have another loopback interface for the router, the routing identification, because it's going to establish communication connectivity via BGP, EVPN. So within these VTEPs, we have different roles, okay? And this is where we see the leaf, which is really where the VTEP resides. My spine, I want my spine, which is my core, to be very, very fast, high speed, lean, very, very quick. It's going to be more IP-based forwarding. It's not going to look at any kind of VXLAN information. Those are the VTEPs. But I also have another entity here of, if I want to get out of the fabric, I have something called a border leaf, a border gateway. And that's essentially a role of how I can actually have intra-site or inter-site or multi-site connectivity to go outside to an external domain, leveraging that VTEP technology. Now let's take a look at the packet. Okay, this is where, to me, I like this stuff. It gets kind of fun. So we have the original Ethernet frame. We're all aware of this, right? The interMAC, source address, destination address, an optional .1Q header if I'm using VLANs. Then I have the original Ethernet payload, and then my CRC checksum to make sure that it's a valid packet. But what we did here is we introduced a VXLAN shim, a VXLAN header. In that VXLAN header now, for my overlay, now I can have my outer UDP. So VXLAN has a well-known reserved destination port for IANA called 4789. That's reserved for VXLAN for the destination address. And then you have your outer IP DA, your outer IP SA, source address, destination address, and you have your outer MAC. But this is the VXLAN encapsulation slapped on top of the Ethernet frame as I'm going through VLAN to VNIs, okay? Now, when I'm looking at this, I'm adding UDP, and I'm adding VXLAN information. So I'm adding an additional primarily 50 to 54 bytes on top of that Ethernet header. So what does that mean? What do I need to do on my interface? Anybody? MTU, exactly. The maximum transmission unit. So really what we want to do, because what VXLAN does not support is fragmentation. So you want to make sure that your interfaces within the fabric have an MTU variable that can support 1500 plus the additional VXLAN header. Thank you for that. And what we're doing here is sometimes, so it's really important to understand, because say you're going over across an SP network for some reason. Maybe the SP doesn't alter the MTU, so you need to make sure you understand the MTU, the maximum transmission unit that's supported across hop by hop by hop, okay? Now, if you look at the VXLAN header, and if we got a magnifying glass, and we want to see what's in this header that makes it so unique, it's really only two important pieces of what really is there. And essentially what you're going to see here is what they call the I flag, and then you have the VNI. Now what the I flag is doing, this is in the RFC. The I flag is in there in the VXLAN header to let the incoming VTEPs know that there's a VNI present. So make sure you honor that VNI and you map it to your VLAN. So if you think about all the R's, those are reserved bits, or the don't care bits, or the all zeros. And the I is the one, the single bit that you're looking at, the information flag. Not only that, is now we're also talking about the VNI, the VXLAN or virtual network interface. This gives me that 24-bit, 16 million segments of using a flexible namespace for segmentation. And this is essentially what I'm using as these 3 additional bytes to be able to establish what that looks like. Now, some platforms will start with the VNI. If you're going to configure, you can start as low as 1. Some implementations may start at 4,000, just kind of a fun fact, but understand that when you're configuring and mapping that out. One thing you will have in my deck, as I'm not going to go over here, but I have all the configurations of my lab inside your presentation here. So you can copy and paste those and get familiar with that, okay? So this is how you configure it. Something simple as this. I create the VLAN 100, and I'm going to map the VLAN 100 into the VN segment of 50,000. It's that easy when you start configuring the VXLAN configuration on those VTEPs. Now, remember when I talked about UDP and that traffic entropy? This is where you kind of understand now, in the IP UDP portion of the frame format or the packet, this is where you'll have your outer source address for IP and your outer IP destination address. And really what this is your source VTEP IP, the loopback interface, say for VTEP 1, and then your destination VTEP IP, which could be VTEP 20. That's essentially how that frame format looks like. And I have a packet capture that'll show you that in an upcoming slide. But when we look at the UDP, remember, the destination VXLAN port is 4789. That's going to tell everybody that this is a VXLAN packet. But on my source port, I want to have per flow. So what I'm going to do is I'm going to take the original Ethernet frame, the 5-tuple, MAC source address, IP source address, destination protocol port, and I'm going to hash this so I can have that random, unique variability within the switch ASIC. Because remember, I don't want that polarization. I want to make sure the traffic is unique and distributes evenly across all of my links. That's very important with traffic entropy, and that's something that VXLAN will give versus other overlay encapsulations. So as I mentioned before, if you think about, this is a packet capture that I did in my lab. Okay, and I love doing packet captures, Wireshark, PCAP, whatever that is, because this understands when you take that theory and you start configuring it, and then this is the evidence. Is it working or not? So if you think about here, host to VTEP, that's going to be Ethernet, right? My host is coming into Ethernet over VLAN 10. So that's the Ethernet header. That's the VLAN 100. It's VLAN 100 actually. This is my IP header. And then what you see here is the payload. Now, the VTEP, when it gets that packet, now it's going to go from the VTEP to the spine. Now I'm going over the VXLAN fabric. So now look what happens. My IP header, you're going to see here that that's left. And now I have my VTEP IP addresses. So my source and my destination of those virtual tunnel endpoints. Within the VXLAN fabric, this is what I'm seeing how the communication is. There's my UDP header, 4789. Now I can actually see the VXLAN header. Within the VXLAN header, I can see the VNI that I'm using that's been mapped for that VLAN 100. So here I can see the VXLAN encapsulation and then my payload. So if you saw how that works from Ethernet to VXLAN, that's essentially the encapsulations that are coming on the Ethernet frame, okay? Now, we talk about the packet format. I showed you a packet capture. The thing is here, as I mentioned before, how do I communicate with you? How do I tell you where my hosts are at? If I have VMs, if I have containers, how do I share those with you? Well, in the past, before we had a control plane like EVPN, we had something called flood and learn. And what the RFC 7348 told you was to be able to support broadcasts, unknown unicast, and multicast, you needed to specify a multicast group in the underlay. So what I need to do is configure for every virtual network interface segment, I need to map that to an IP multicast group. So if you're interested in, say I'm sending some kind of broadcast channel, you want to watch a live stream of somebody talking, we're doing a multicast feed. That's essentially how you have to be subscribed to that channel in that group. And I'm going to be able to deliver that packet technology across the fabric. But it wasn't intelligent. It was cumbersome, but some customers would use this in the underlay and use PIM to be able to support that for broadcast, unknown unicast, and multicast. You have to make sure we understand there's not just unicast traffic, but multi-destination traffic, right? Another way we handled multicast or unknown unicast or broadcast traffic was using something called head-end or ingress replication. Now, what that does is that puts a lot of burden on the VTEP. Because the VTEP, what it has to do, it's more of a unicast method than a multicast, but I have to replicate every packet. So if there's 120 folks in this room, and you all wanted that 20 meg of traffic, then I'm sending one copy to each and every one of you. So it's not ideal for a large network. Maybe for something much smaller, but it's not necessarily ideal for that because it's a lot of tax and a lot of load on the switch kind of algorithms and processes, okay? So why VXLAN? How did we get here, right? We wanted to go beyond those 4,000 VLAN limitations. We wanted to support things like VM mobility, the vMotion. If I have a server, a VM, my server is getting high power, there's something wrong with it, and it's a very critical application. Maybe it's something for billing. Can I take that virtual machine and move it to another device without having to re-IP it? That's what vMotion is. So it's really good for disaster recovery, but resiliency, and gives me a level of uptime. And so that's what we wanted to do, is have the ability to do that. And what VXLAN delivered was seamless VM mobility, leveraging equal cost multipath, no more block links like Spanetry did. And then we had the ability to do any workload anywhere and have true address isolation. And that's what's important here, but we weren't finished yet, because this is just the data plane encapsulation. What did we need? We need the control plane. And the control plane of choice for the data center is EVPN, Ethernet Virtual Private Networks. Now, EVPN has been around for quite some time. And if you think about here, this is the standard, the RFC 7432, but there's different data plane encapsulations that are tightly coupled with EVPN that we saw from service provider networks like MPLS, Provider Backbone Bridge, and then ultimately network virtualization overlay based on that draft. And so that's what we needed to really take the significant and value add of the VXLAN data plane encapsulation and marry it to the EVPN control plane. And so this is essentially where I can have now some intelligence. My control plane, my CPU complex, has the ability to kind of share the information of MAC and IP. So this is where we have a protocol that can do not just IP, but the MAC address, and also have some MAC VRF, virtualization, routing, and forwarding capabilities for isolation. So these are the route types for EVPN. Okay, there's more than that. There's going to be, I think there's 12, there's many more than that. But what I want to focus on are these two route types, because these are the most important ones. These are the ones you see in your lab. If you do show commands, you're going to see a lot of route type 2s carrying MAC and IP, or MAC only, and route type 5s that are going to be more of an IP prefix subnet advertisement. Because this is where I want to share information across the network and the fabric. And how I do that is by having some form of intelligence in the control plane to deliver that. So what we did with BGP, EVPN, here's some terminology here. And I like to give the analogy is, for me, I flew in from an airport, right? And if you think about the airport, it's a common infrastructure, but you have different airlines. Maybe you have Virgin Australia, Jet Air, United, Lufthansa. Different airlines, but they're maybe sharing the same common network. These are all different tenants. Maybe in your business, you may have marketing as a tenant, development engineering as a tenant. So you need some kind of isolation, but maybe you have shared services where you need to have people have the same access to different things. So what we're doing here is we're creating a control plane protocol that mirrors what we did with the virtualization of the server, now we can actually leverage things to support compartmentalization of the routing table. So now I have a single routing table. I have something called a VRF, virtual routing and forwarding, where I can essentially carve that routing table out and say, you get this routing table, you get VRF A, you get VRF B, you get VRF C, and these are all your own entities. And you can have overlapping IP addresses. Say you and I, we bought a company, and this company is using the same subnets as we are. We don't want to re-IP everything. We want to make sure we can just slap a different identifier on that and have an easier way to kind of use virtualization and isolation and segmentation. So what we introduced was VRFs, but then we also wanted to make sure, how do I give the routing information a unique variable, a unique entity? And this is where you see something like a route distinguisher. And that gives me a unique field where I can actually give some unique value leveraging an autonomous system and maybe a VNI together. And then ultimately, I have the ability to kind of implement policy with my route target to give a nice import-export of routes across different entities. Because maybe I want to populate certain things that they want access to. And that's essentially what we did here, leveraging multi-protocol BGP, and this is what EVPN is able to support. So within EVPN, you inherited multiple things. So you can see here in my example from a leaf spine, what we also introduced was the concept of a route reflector and a rendezvous point for multicast. Because we didn't want to have BGP to be full mesh here, so we had to make sure we developed some kind of mechanisms on the spines to support this. Now, inherently, EVPN allowed us to support these functions. Now, who here has heard of Anycast IP Gateway? So what this is, essentially, this allows me to support things like a distributed or a VM motion type of entity, because now on all of my Leaf devices, I can have the same default gateway IP address for that SVI. So I configure it across all of my fabric, but then essentially now those things can be portable, they can move around, and they can essentially have that same connectivity so that it's very much seamless. And then I can support things like ARP suppression. So if my VTEP has a local ARP cache, instead of flooding it across the entire fabric, now I have something more intelligent and smart, and I can actually ARP on behalf of somebody else back to that endpoint. So what we're showing you here is VXLAN as a data encapsulation was good, but it wasn't great until you marry it and tightly couple it with EVPN. And that's what's needed here. So what you see, so now that I have the data plane encapsulation, how can I actually do this host discovery? How do I leverage the control plane to build a table? So this is the overlay fabric. And what we have here is we want to have host distribution, because we want to make sure that instead of having, as I mentioned, all of the leaves running a full mesh of IBGP, let's just have it on the route reflector, which is the spine, and that'll radiate down to the route reflector clients, because it's much more lightweight and conversational. So what I mean by that is it's going to go ahead and all the leaves are going to send these information to the route reflector, and then the route reflector will send it to all the VTEPs. And that's how it works. So I'll show you an example of what that does, but the different types, like as I mentioned before, route type 2 for EVPN can just, it's mandatory to carry the MAC, and then it can also carry MAC and IP. If you have your MAC address and your IP address, your /32, you can actually transport that. So you have a combination of both. And then if I have IP subnets, I can actually have an external domain to support that, leveraging route type 5. So let's see how that works. I have 3 hosts, just for this example. Host A, host B, host D. And all I see is the 3 different MAC addresses. I don't see any IP address information now. So what I want to do is I want to build this table. Okay, I want to build the control plane. So Leaf 1 is going to send out an EVPN route type 2 update to the route reflector, and it's going to build this table out. So if you can see the table, I'm going to populate that with route type 2. I'm putting the MAC address here in its length, and then I have my layer 2 VNI. This is what I map my VLAN to. My VLAN is going to map from VLAN 100 to VLAN 3001, and then here's the BGP autonomous system number and that particular VNI. And then my next hop interface is where I learned that from. So 10, 200, 200, 101 is essentially this leaf here. And this could be 102, 103, 104, etc. So when I do that now for leaf 2, same thing. Route type 2, different MAC address, same layer 2 VNI, different next hop, and the same thing for leaf 4. So I'm building that table to establish communication, because what I'm going to show you is how does a packet traverse the fabric. And so what I've done is I've carried just the MAC information. In the RFC, they use the labels from MPLS. That's a layer 2 VNI. And then I have this route target for essentially a MAC virtualized routing and forwarding table. Now, what about layer 3 traffic, right? Because remember we said integrated routing and bridging, the best of both worlds. Now I have a MAC and an IP address for my hosts. So my MAC addresses are here, but now I've introduced the IPs, so it's still going to use route type 2, because that's optional. So now what I'm going to do is still send the route type 2 update to the spines and build the table, but I'm filling out more information. Now I have an IP address and now a layer 3 VNI with my next hop interface. So I do the same thing across the different VLANs or the different VTEPs, and I build this table out. And what this is going to do is it's going to allow me to have that communication over my VXLAN fabric. And that's why it's important here to show that. This example here is, say I just have subnets. Say I have subnet A over here, 10.0, 10.0, and 20.0. I can essentially do the same thing. Now I'm using a different route type for that connectivity to get outside. And that's what that looks like. You have your route type 5s populated with the IP, the layer 3 VNI information, and your route target with your next hop interfaces. So what we want to show is, let's show how a packet walk works within the same VNI, the same VLAN, okay? So if you look at this drawing that I created, I'm just really making the VTEP much bigger, okay? And you can see here that I have two different VLANs, VLAN 10 and VLAN 20. Now those have an SVI configured on there. You can see here on 192.168 1.1 and 2.1. Now host A wants to talk to host B, and they're on the same layer 2 the same subnet. So what's nice here is I'm going to go ahead and send that traffic. So the first thing that's going to happen is this host is going to generate traffic leveraging its source MAC and IP MAC, but the destination MAC is going to be the destination MAC of this host B, because it already has the ARP table populated, okay? So what's nice about that is it comes in via Ethernet. This is the Ethernet frame. Now what happens here is the VTEP does a lookup, right? It gets the packet, it gets the frame, it does a lookup, and it says, hey, I see that destination MAC address is mapped to VNI 3001. So what I'm going to do is I'm going to take that, I'm going to perform the lookup, I'm going to map VLAN 10 to that particular virtual network interface here. So what I do now is the VTEP encapsulates that Ethernet frame into a VXLAN packet. And now the packet is transported to VTEP 2 over this virtual wire. This is over the overlay. So now we're going from Ethernet to VXLAN, showing this level of layer 2 adjacency, because these could technically be in another city. It doesn't have to be next to each other on the same port. So this is what we're doing here, is we're building that layer 3 underlay to take that overlay services to make it integrated routing and bridging. And here I'm showing you bridging over a layer 3 fabric. So now we have the VXLAN end caps. The packet is transported. The underlay is going to route the packet based on that source IP, destination IP address of the VLANs or the VTEPs that are configured. So you can kind of see here, this NVE is configured here, this IP address, and it's also here. And that matches my source and destination. So that's what I'm routing by in the fabric. Now, when the VTEP receives that packet, it's going to perform a lookup too. And it performs the lookup and it says, hey, that MAC address is locally attached to me. So what I'm going to do now is take that VXLAN packet, I'm going to strip that VXLAN packet, decapsulate it, and I'm going to map it into an Ethernet frame. and keep it just like it was with VLAN 10, the source MAC and destination MAC, and the source IP, destination IP. So these two endpoints had no clue they just went over a VXLAN fabric. To them, they're just kind of sitting on the same Ethernet topology. Does that make sense? So that's how we developed this VXLAN technology. And that's why the packet walk kind of brings it all together. But you had to have a control plane to understand that. Now let's say if I wanted to communicate across a layer 3 network, how does that work? Same scenario, but now host A wants to communicate with host Y. So now we have some more information. Right now we're talking about we need to do some routing. So if you look here, what's different? I introduced something called VNI 50001. How many of you out there have heard of something called symmetric IRB? This is something that's part of the VXLAN standard, part of the EVPN technology. But essentially what you're doing is you want to make sure that the VTEPs can bridge and route, and it has the same kind of traffic patterns between source and destination. So what we're doing here is, for this case here, I need to route. So host A generates this traffic. What's different though is the destination MAC is the Anycast gateway, the EVPN configuration protocol that you need to make sure that you have for that VM mobility. But now I need to route. So because I'm using the DMAC as the Anycast gateway, when the VTEP gets it, it says that's me. So I need to route this packet because this isn't something I have locally built. So now what the packet needs to do, it punts it to the route processor on that switch. And what the control plane and CPU are doing is says, okay, now I need to route this packet. So what I need to do is take that packet, do my lookup, and in my lookup, I can see here that where this sits and where this resides, I have my routing table populated for different MAC IPs, my layer 2 VNI, and my layer 3 VNI for these particular VTEPs that I know about based on this information. So because of the control plane, I have this knowledge. So what I'm doing here is because I can look it up, I say, okay, here it is. This is the MAC address. That's the IP. This is the layer 2 VNI if I wanted to bridge. This is the layer 3 VNI because I need to route. So now what I'm doing is, okay, so now the VTEP knows it does the route lookup. It's going to go ahead and update the destination next hop, router hop, and the source MAC as its own. And then it's going to still carry that over the wire and encapsulate that into VXLAN and send it over this virtual network identifier with using this 50,001 for layer 3. Because now, this is what I'm showing you here. Because I'm doing layer 3, I can have multiple VLANs belonging to the same tenant. So imagine that this is, two different VLANs mapping to this particular airline, both here for VRFA across. Maybe this is Virgin Australia. But I have different VLANs for different subnets for different connectivity. So I send that across, and my underlay network is going to route the packet based on that outer IP header. And then what happens to the remote side? The remote side is going to do the same exact lookup. It's going to see in its table, because it's going to see that it has the destination MAC address being its own. It sees the DMAC being the DMAC of the VTEP2. And then because it does the lookup, it sees it's there. It determines that packet is mapped to this particular VRF. And then it sends it from the VXLAN, and it decapsulates the VXLAN header to Ethernet. And then again, it rewrites the MAC address and sends the Ethernet frame to this host. So I know it's pretty complex to see a lot of this stuff, but that's essentially how you would do layer 3 transmission across a VXLAN overlay fabric by leveraging the layer 3 VNI here to establish that connectivity across the different VTEPs. Can you believe it's almost been an hour? Wow. So what did we learn? What we learned is VXLAN was awesome as a data plane encapsulation, but it only used flood and learn initially with RFC 7348. What we needed was something like a control plane like EVPN that can have a tightly coupled integration to do the mapping of fabrics, to support the VM mobility, to support the default Anycast gateway, to support things like ARP suppression. These is where you can kind of see that there was a marriage that was required from a data plane of VXLAN to a control plane like EVPN. And this is what we saw is with VXLAN, we got around spanning tree. We can use all active uplinks. We built a layer 3 fabric and built an overlay technology. That's why VXLAN is the de facto standard for the data center for an in-caps. This is essentially what we're talking about here. So I went through the challenges of the applications, how they were written, and how the network needed to evolve. And then we talked about the different overlay taxonomies with underlays and the VPNs. And then what we kind of showed you is with this VXLAN now it can do 16 million segments of how it can support more scale. And essentially, you probably hear it more and more time again, is EVPN is the better control plane with VXLAN. I would encourage you to attend different sessions. I will be speaking at another session tomorrow morning. I believe it's 2667. If you want to sit more, it's a 90-minute session on more of the VXLAN leaf topology and information. These are all hyperlinks for recommended reading. Remember to use the WebEx space. If you have any questions, I can feel free to talk to you even after this session, or I have to meet the engineer. You can schedule some time with me. What I need from everyone to do here, though, is to complete your session, complete your survey. Typically what happens is people will complete the survey, but then they'll get pinged and reminded because they want to get a T-shirt or something, and they may forget, like, who was that guy again? Oh, whatever. That happens, right? I know people do that. But just complete your session, because this is my 3rd time in Australia, and I love coming here, so if you guys want me to come back, if not, it's all good. But continue your education. Please visit the World of Solutions, look at the demos, do these walk-in labs. There's some VXLAN labs. There's Cisco modeling language labs that you can actually leverage. There's a lot of things that we can do for packet captures and capture the flag. So that's my time today. We did an hour. Thank you, everybody, for coming. I appreciate it.